I think it might be worth it that we spend some time to go over what we previously discussed. So the key idea is still there many electron wave functions, right? And there, I want to discuss some of the key points we learned in the previous 3 to 4 lectures, because we have been touching on the term symbol many wave function actually in the past 3 or 4 lectures, and maybe sometimes we get confused, but I just want to point some of the key conclusions we get, right? A very useful and the simple case is excited helium, because this is probably the most simple many-electron system we can find. So it has the 1s and with another 1s excited to the 2s orbital. Right? So this is basically just a 2-electron system, very simple. But we can learn a lot of things from it. So because during the process, we've shown that there's some fundamental requirements, right? I just want to emphasize this again. We need to keep in mind electrons are fermions. So this is a very important fact that will actually have a lot of fundamental effects. Because of their fermions, so the wave function must be asymmetric. We explained that. What does it mean to be asymmetric, right? So there's a very rigid physics definition about that. The whole wave function does not change upon the exchange of the 2 electrons, right? If we change 2 electrons, the wave function itself, I'm sorry, it's asymmetric, so it should be changed. So there should be a minus sign in front of the function after operation. If there's no minus sign, it stays the same, then that is symmetric. So that's the definition of symmetry in physics or in math, meaning that the system does not change upon some certain operation. Okay, because of this kind of requirement, then we realize that we cannot use some simple multiplication between 2 basic wave functions to obstruct our solution. We have to construct a certain form of the linear combination that can at least satisfy the fermion or the asymmetry requirements, right? So that's why we want to pay those efforts to construct a certain form of linear combination and to satisfy this kind of requirements. And in fact, we also have some additional points. We talked about the electrons, they have the Pauli exclusion principle, so that we cannot have the same pair the electron that with all the quantum numbers are the same, including the spins, right? So that's also a requirement. And also we know their electrons are indistinguishable. They're more abstract and more physical. And you can check the previous lecture, what does they mean, but they all comes into the final form. Okay, because of this specific form of the wave function, and if we plug this kind of a wave function into the Schrodinger equation or into the Hamiltonian operator, so we can calculate the energy, right? And we can calculate the energy for those wave functions. Then we realize actually there's a so-called, I'm sorry, this is a typo again. This should be singlet, not a single. A singlet energy corresponding to this E0 plus J plus K. And there's also triplet energy, which equals to E0 plus J minus K. And this is a very interesting result because E0 corresponds to the system where there's no interaction between electrons, right? So that is the E0, some sort of the basis. But both of them have this plus J term, and this J comes from the Coulombic repulsion between electrons, right? So because electron, they're always repulsing each other, so actually we have the plus term, plus J term. But the different from each other in there is K term, and the K is actually the exchange interaction. So if the 2 electrons, they have the same spin, actually they will lower the total energy of the whole system. And we also discussed this kind of application of exchange energy in determining some of the 3D atoms, right? I think we talked about why sometimes the 3D orbital is filled first before filling the 4s orbitals, especially for those half filled or the full filled the elements. Okay, so this kind of form leads us to this kind of conclusion that we know this kind of exchange interaction arise, and we can see this is a pure quantum mechanical. It doesn't have any analog in the classical picture. Some other key points for the many-electron system, I really want to emphasize this because I do not really see any lectures. Yeah, maybe I missed some, but I do not really see people emphasizing this when people are explaining term symbols or explaining many wave functions. But I really want to emphasize this because people tend to have this sort of electron structure diagram, right? And this is very typical, very useful, especially when we talk about the molecule orbital diagram. So we have the, for example, the sigma bonding orbital, anti-bonding orbital, and a pi bonding and anti-bonding. They're very useful for us to understand the electronic structure of molecules. But when it comes to the many wave function, there's a pitfall for that, because the electron structure diagram that we draw to express ideas may not be, in fact, a valid wave function to satisfy the many-electron Hamiltonian. And the reason is something I explained before, because we need to respect the fact that the electrons are fermions. So one example is still this excited helium, right? We went through a lot of our mathematical derivations, and I mentioned that there's a MIT physical chemistry course, which is very helpful with all the detailed mathematical derivations. And we skipped that, but we learned that finally we can reach the conclusion of this singlet state and this also triplet state. And if we corresponds to the specific wave function with the diagrams, we realize that this singlet in fact corresponds to a linear combination between the two diagrams, right? So we can put electron in this way, we can put electron in that way. So this is some kind of a spin down on 1s and spin up on 2s. And this is the opposite. It's a spin up on 1s and spin down on 2s. And the singular wave function, in fact, is a linear combination between them with a minus sign on the second term. And for the triplet, in fact, we do see something that is easy to imagine. For example, we have this kind of parallel spin, right? They're both spinning down. So we mentioned that this can give rise to the exchange energy that can lower the total system energy, right? So we can easily associate it. Okay, we can understand this should have a low energy because they have a parallel spin, right? And this one, likewise, also should have the low energy because they also have the parallel spin. But this one may not, I think, doesn't really seems to be intuitive if we do not go through the detailed mathematical derivations, because this is also a linear combination between the two states. It's just neither pair up or they're parallel. So the conclusion is still this sentence. We need to be careful that at least we need to appreciate this kind of convenient electron structure diagrams doesn't necessarily mean they're a valid wave function, right? And the reason is for this kind of a pair electron configuration, we can draw to show it, right? But this one implies that we actually will write the spin part as this kind of a form. So alpha means a spin up and beta means a spin down, and sigma 1 means the coordinate of the first electron, and the sigma 2 means coordinate of the second electron. So this kind of a pair wave function for the spin part cannot be part of the many electron wave function because it doesn't satisfy the asymmetry requirement. Okay, so I repeatedly saying that we have this kind of asymmetry requirement, and that would have a lot of consequences on what kind of a form the wave function may take. Okay, so we also talked something about the term symbols, and I emphasize that term symbols is a powerful tool or a powerful way for us to understand spectroscopy, because the spectroscopy relates to the energy levels, right? Even spectroscopy aside, we still care about the energy levels of the many electron system. And with all those, previous conclusions, I think everybody has impression that many electron wave function is complicated. It has this and that requirement. It has this that kind of a linear combination, and it has the spatial power, spin power. Those also are complicated, but term symbol provides a very convenient solution, at least in terms of the energy level, because each term symbol can be related to a specific energy level. So what does this mean? This means that we can learn the energy levels without knowing the detailed wave function. For example, in the case of the excited helium, so we can derive the term symbols from the 1s1 and the 2s1 without really solving the Schrodinger equation. I think that is something that is very powerful about the term symbol. And we also need to appreciate that this works because there are some of the fundamental quantum mechanics, the principles, specifically the spin and the orbital angular momentum operator, they commutes with the Hamiltonian. So this definitely would involve some of the detailed linear algebra mathematics. I think we explained that in the previous lecture, right? What does it mean that two operators commute? And what does it mean that for the spin or the orbital angular operator and for the Hamiltonians? So no matter how much you want to go into the depths about understanding them, but at the very least, I think we need to appreciate that because those operators, they commute. So actually they share the same set of eigenfunctions, right? So we do not know what specifically those eigenfunctions are, but we know those will share the same pool of eigenfunctions. And those eigenfunctions are the many electron wave functions we are aiming at. So, so that's why we can really resort to this term symbol tool to understand the energy levels of their many electron systems. And we also introduced the term symbol specifically. I think if we still remember, this is a 2s1 term. Is on the upper left corner, and this S has specific meaning. This S is actually the total spin of the whole system. For example, it is the parallel spin, and so it actually should have for example, the S equals to 1, right? So actually, because the spin itself is a half, so two parallel spin, that would be 1. And then we put this. We do not put S here, but I think last time somebody asked why we go to the put more extra effort and put the 2s1 instead of just S here, because 2s1 is maybe more useful than 2s, because from 2s1 we can directly tell the multiplicity of this term. So for example, if we derive the term symbol for the excited helium, then we can actually realize that the triplet would have actually the 3 here, meaning that it will have the 3 states corresponding to the same energy, and that's why it's called a triplet, right? And also you can think about the scenario and you realize that actually S does equal to 1 in that case, but we would put the 3 here because it corresponds to the degeneracy of this whole thing. Whole term, so which is more convenient to read. And L stands for the total orbital angular momentum. That's basically the vector coupling between the different electrons. And J is the total angular momentum. So that's including both the orbital part and the spin part, right? And another thing is for the 3D elements and also for this lower atomic I mean, the first row or the second row or third row, they all have this kind of negligible correlation between the spin and the orbital. So actually, they also satisfy the so-called the spin orbital coupling. And so a typical case arises in the, for example, in the L edge, right? So we know that L edge has the L2 part and L3 part. And that's specifically for the transition metal L edge, since we're exciting from the 2P and to the 3D. And we have L2 and L3. Why 2 and 3? In fact, 2 and 3 corresponds to the way the spin and orbital they couple together, they couple with each other. So if it's a 3, in fact, they can couple constructively. So it's actually the L3, and for the L2 is actually the spin and orbital can construct destructively. So actually they have two, and that's why actually the L edge is composed of 2 parts, and also associated with how this total angular momentum arises. Okay, I took snapshot from the website. So this is our website that was a lot of their explanation about the physics, including the spectroscopy. So I think this picture is very straightforward. So actually, I directly borrowed from the website. This is giving us example of the carbon. So we know the carbon has this sort of configuration, right? And this is also typically how the electron configuration is written in the periodic table. Through the term symbol, in fact, we can understand the energy levels of this many-electron system. So this is a many-electron system, right? So we have the 2p2. We may not have thought about it, but if we think about it, how those 2p2 they're arranged, right? Even in the simple picture of the electron diagram, whether they are residing on the both residing on the 2px or 1 px and 1 py, or 1x px or 1 pz. Actually, there's several configurations, several possibilities of how this 2p electrons can be arranged. Probably we have may didn't think about that before we come to the many-electron wave functions, but this is actually a valid and a practical question. So through the derivation of term symbols, in fact, these symbols can be directly derived by analyzing the microstates. I think previous lecture, I promised that we will go through the microstates, and you can also search online in how to do the derivation of microstates, which is kind of lengthy, probably would take about 10 or maybe even more minutes to really for us to go through all the details. But I want to tell you that deriving term symbols is much easier than really solving the many-electron wave function, right? So it's definitely still worth it. And through the derivation of term symbols, in fact, we can derive all these term symbols. Actually, you can see they have their different states. So our job is really to understand which is ground state, right? Which corresponds to the lower energy. And other states, in fact, corresponds to the excited states of this carbon. And this is many-electron system. So as this says, we first look for the maximum multiplicity, which is the 2s1 term, right? So we mentioned that the 2s1 equals to the multiplicity, and apparently these 3 terms, they all have the multiplicity of 3. So actually they are all triplet, right? So we have this triplet here. Then if they are the same, they are all 3, then we look goes to the L part, which is the total orbital angular momentum, right? So that's L relates is associated with the orbital part. So we look for the largest value of L. So if you still remember when L equals to 0, we have a S symbol, right? And if L equals to 1, we have the P symbol, right? And if L equals 2, that corresponds to the D symbol. That's basically how we correlate those symbols with numbers in a picture of atomic orbitals, right? It's basically the same, just we have the capitalized letter. So we look for the largest L, and apparently, this P, but they all have P. So actually, we'll go to the next one. But if we compare this one, for example, if this is 3, then we know that compared with D, actually this one has this D will have lower energy because the L is larger, right? But now the L is the same. Then we go to the third part, which is the total angular momentum, which is considered the coupling between the spin part and the orbital part. So for less than half filled shells, which is the case here because we have the 2 electron in the P shell, we look for the lowest value of J, which has the lowest energy. So apparently this one has the J equals to 0, and this one has the J equals to 1 and equals 2. And we arrived the conclusion that this 3P0 is this triplet P0, in fact, is actually the ground state for this carbon. And in fact, if you're more interested, you can think about what does this mean if we think about the electron configuration. So in fact, you arrive some interesting conclusions about in the ground state how the electrons are arranged. Okay, the second part I just want to briefly show you actually there's another related term symbol, which is a molecular term symbol. So for atomic term symbol, we think about a single atom that has many electrons. And in fact, I think in the literature of the spectroscopy, it's very common that you may also come across the molecular term symbol when people are discussing about the lines for some molecule or for some solid systems. So I think we just briefly just also mention this part. It's very easy to correlate. So we'll go probably quickly on this. So this is typical atomic term symbol, right? And this is a typical molecular term symbol. And the correlation is very easy. So for atomic term symbol, we have the L values that corresponds to the different letters, English letters. So we have went through this previously. So for the molecular term symbol, it's actually the same. So instead of calling it L, we call it a lambda. So you can recognize this is the capitalized Greek letter of L, which is lambda, right? So if lambda equals to 0, then we call it a sigma. So you can naturally think this is sigma is actually the Greek counterpart of S, and it follows that the Greek counterpart of a P is pi, and for D we have the delta, and for the F we have the phi. So it's basically just the Greek counterpart of English letters in the atomic term symbols. And also for the atomic symbols, we also have the total magnetic quantum number, but this is not the same as in atomic case, which is not easy to derive. Sometimes it's impossible to derive. And also we have this total spin magnetic quantum number, MS. MS is can be derived for the molecules, and basically follows the similar philosophy of what we do for the atomic cases. And those are the detailed operations. We'll see if we can find some time to discuss later. But there's more information about the molecular term symbol. So I think, as you can tell here, this corresponds to the multiplicity. This corresponds to the total orbital angular momentum, and this corresponds to the parity. So maybe you are familiar or may not be familiar with the parity, but I think this is also a very important concept and something that we can commonly meet in learning the electronic structure of the materials. So parity simply means it's a symmetry. with regard to the inversion, right? So if we have an inversion center, we actually we move this XYZ to the minus X and the minus Y and the minus Z. So if the whole system is symmetric with regard to inversion, we call this Gerardi. I guess that's I'm not very sure about the German pronunciation, because this is actually has the German origin. So in German language, this means that it's symmetric. So that's why we have the G symbol standing for symmetry. If it is asymmetric with regard to the inversion, then we simply just cut on Gerardi and short term as the U. In fact, G-related their orbitals having the G symmetry is very common. So this is you can easily tell this is basically their sigma bonding, right? So we have the sigma bonding, we have the overlap, we have the head-on interaction between two atoms. So you can tell this is actually symmetric with regard to the inversion, and this is a G orbital, right? So in the context of molecular orbital diagram, it could be like a 1 sigma G or 2 sigma G, but well, we can appreciate this is a G orbital. And for the P interaction, for the pi interaction, so we can tell this is actually a pi orbital, but it is not the bonding pi. This is the bonding pi, right? This is the anti-bonding pi because it has the nodal plane, right? So it actually is anti-bonding in nature, and those are out of phase. So this is our anti-bonding pi orbital, and it's actually also a G orbital in nature, right? So we can tell they are symmetric with regard to their inversion. These two are very common for the transition metal oxides. So we talk about the T2G orbital or the EG orbitals a lot, especially for the transition 3D transition metals. And this is basically showing how the orbitals look like spatially. So you can tell, in fact, because the center is here. So this is our T2G. We have, for example, we have this DXY or the DXZ or the DYZ. They're interacting. So these are the oxygen. So this is transition metal. This is oxygen, and they have this sort of action. You can tell that they have this kind of a shoulder to shoulder, right? So this kind of shoulder to shoulder, and same here. And same here, this sort of a shoulder to shoulder interaction that is naturally associated with the pi bonding. And you can tell this is in fact a G symmetry, because you can tell this in fact corresponds to here. So if we do the inversion symmetry, in fact the whole electron wave function will not be changed, right? The same here is all inversion and symmetric. So this is actually has the G symmetry, and because in the context of molecular orbital, it's not the first T orbital, so actually it's the time mentioned. So that's why it actually has the 2 in front of it. It's actually T2G. And there also for the EG orbital, it also is in fact is also G in nature, right? If we look at this kind of diagram, we can tell the same transition metal here, oxygen. Let's say the ligand is oxygen, oxygen here, and we can tell this is also symmetric with regard to the inversion. And there also you can appreciate that this is kind of a head-on interaction, right? So this should be a dx squared minus y squared. So we have this kind of the lobes pointing to the orbitals of the oxygen. So we see this is a head-on interaction, right? And this is symmetric with regard to the inversion center. So this is actually the EG orbital. So those are common G symmetry orbitals that we can meet in some of the common systems. We also have this this kind of a U orbital, which is actually asymmetric, right? So this is a sigma antibonding. So this is head-on interaction, but we can tell this is a antibonding in nature, because this is a nodal plane in here, right? It has a nodal plane, and also those they actually destructively interfere. This is out of phase. And so this is actually U symmetry in nature. And for this sort of a pi bonding, so this is in pi bonding, right? Because we see the electron cloud overlapping. So this is a pi bonding. But if we think about the symmetry of this in the framework of our inversion, we can tell actually this would change to here. So it would change the sign, and this is actually a U symmetry. So we know that for this kind of a diatomic system, the pi bonding orbital is in fact a U symmetry in nature. Okay, so this is what we mean by parity and how to think about the common the molecular orbitals in terms of this parity definition. Okay, so yeah, I think that's in fact pretty much I plan to discuss today. And just another want to mention, I didn't pre-slide this one, but I want to mention this plus and minus sign corresponds to the symmetry of reflection. So for the reflection, I think it's the more straightforward, right? It's when we have a defined a symmetry plane, and if we just do the reflection, and if the system doesn't change, and we have the plus sign, and if the system changes and turns to, so we have the minus sign here. So it captures implicitly the parity and the reflection symmetry all in this molecular term symbol. So my plan is for the next lecture, which I don't know, could be sometime later, we will directly go to the analysis of transition metal L edges. So if you haven't installed the software called the CTM for XAS, let me see if I can write it on the, I don't know if there's an option for me to write. Anyway, I'll type in the chat box later. So if you can install the CTM for XAS software, it can be easily searched online with the detailed installation instructions. We can go through some of the typical transition metal LH spectrum calculation. And we can relate what we learn about this term symbol and with what really appears in the software. So that's sort of my plan for the next lecture.